Sorry. Okay, you're gone. Okay, so next speaker, Briley Lewis, talking about GPU-enabled debris disk modeling with GRaTeR.
Thank you. Can everyone hear me okay? Okay, great. Hi, everyone. My name is Briley Lewis. I'm an NSF postdoc at UCSB. And this is some work that I've been doing with Max Miller-Blanchard and other members of his group, where we are actually using GPUs to model debris disks super, super fast. So I know we've been in data processing and point source mode for the most of the day, so a little refresher on debris disks, even though we did hear about these yesterday. So debris disks are our exo-Kuiper belts. They're this later stage of planet formation and evolution, particularly the evolution part, where now the system is optically thin, it's dust instead of gas, and it's dust that's replenished by collisions. So why do I care about debris disks? Like I said, this is a stage of planet evolution. So the interesting thing here is we get to look at the dynamics of the system as planets are migrating. This can be seen as analogous to like the late heavy bombardment in our own solar system. So this is, where Earth would have been getting its water. So it's a really interesting stage to look at if you're thinking towards habitable systems. These are also optically thin, like I mentioned, which is particularly useful because it makes them a lot easier to model than protoplanetary disks where you have to do full ray tracing to really get a model. We can also learn about composition for these disks because we can see all the way down to the midplane because they are optically thin. And debris disks are essentially proof that planet formation was able to happen where we see dust because that dust is the remnant from planetesimals that have collided with each other. So we're talking about debris disk images in scattered light in this talk. So debris disk images, to understand them, we really have to make models of disks to know what's going on here. So there are a lot of existing debris disk modeling tools. There's sort of two main groups. One is analytic models. So these are not doing full ray tracing. Instead, you have like a dust distribution. The canonical example of this is GRaTeR, which people have been using for quite a while now. And then there are also these ray tracing codes that people also use for protoplanetary systems, like MCFOST and RADMC3D. And then more recently, there's also Winnie, which is basically GRaTeR, but make it JWST. And so a problem here is that a lot of these codes are quite slow. And because of that, if we're trying to do full MCMC fits to data with these, we have to make assumptions on some of the many parameters that go into a debris disk model. And so, okay, we're making assumptions about things that we're not 100% sure how they're degenerate with each other. That's kind of a problem. And we do think that a lot of these parameters are degenerate with each other. And so our solution to this is this package called GRaTER-JAX. So it's GRaTER, but make it JAXed, and I will explain that. So it's a really fast debris disk modeling package, and I wanted to acknowledge specifically a computer science undergrad in our group, Mihir Kondapalli, has put a lot of work into this package. So JAX is how GRaTER-JAX gets its speed. This is a Python package that is almost a drop-in replacement for NumPy. So instead of doing import NumPy as NP, you can do import jax.numpy as JNP. There are some sharp bits that I can tell you about if you want. So it's not quite that simple, unfortunately, but it is still pretty straightforward. And from using JAX, you get all of these benefits. So we can use GPU computations, where we're using graphics processing units instead of traditional CPUs, and we can parallelize things and make them super fast. We can do just-in-time compilation, where the most used parts of the code that are used over and over again are actually compiled down into machine code so that you can run them faster. And then there's automatic differentiation, which we heard about in a bunch of the talks this morning. So GRaTER-JAX is 39 to 59 times faster than previous implementations of GRaTER models, which is kind of a wild speed up and really compounds when you're doing, maybe millions of these models for an MCMC fit. And so this is compared specifically to the implementation of GRaTER in the Vortex image processing pipeline. So the ingredients for a GRaTER-JAX model: we have the dust distribution, which has all of the different morphological parameters of the disk. So we've got, there we go. We've got these inner and outer power laws that govern the dust distribution radially, the inner and outer edges of the disk, the position angle, the inclination, and then there's also all of these different vertical profile parameters of the disk. So the scale height, gamma, that describes the vertical fall off, and beta, the flaring parameter. So beta, gamma, scale height, these are some of the ones that are not fit for as commonly because you have to make choices when you are limited by computation. The other half of what goes into this is a scattering phase function. So Christine actually showed this plot yesterday in her talk. This is showing the different scattering angles that are visible in the HR4796A disk. And so the scattering phase function really just describes what is how efficient are the dust grains at scattering light at different angles. And so this is a really important part of these models. This is an example model. So this is some of the GPI data from GPI 1. This is HD117214. You can see we get an absolutely beautiful fit here. I will say, so JB mentioned earlier that modeling extended sources is really hard, especially when you have self-subtraction. We're kind of sidestepping that issue here by using polarimetric data. So we're not having to deal with the self-subtraction of doing PyClip or something like that with RDI and ADI, because instead we're doing PDI, which is very fun. And I'll use this as an opportunity to shamelessly plug Rebecca Zhang's poster that will be in poster session 2 that talks about NIRC2 polarimetry, another thing that we've been working on in this group that will be awesome for disks. But so this is an example GRaTeR-JAX model. And to recap, GRaTeR-JAX is fully open source, so it is available on GitHub. We're really committed to open source software in this group. It's accelerated with JAX and GPUs, so it's very fast. It's complete with both the disk model itself and optimization tools that work nicely with the disk models all in one. And something that I think is really cool is that it's able to model scattering phase functions as a spline instead of with traditional methods. And I will go into this. So this is a plot of a couple empirically derived phase functions for different disks from Meredith Hughes' 2018 review paper. And it shows how a couple different Hennier-Greenstein functions don't quite match the data that we see. So Hennier-Greenstein functions are this empirical function that has been used to describe disks. They're parameterized by G, the asymmetry parameter, and they just don't fit the data that well from what we see. So this is one function with one asymmetry parameter that can capture the backscattering part of the disk. This is a different asymmetry parameter, Hennier-Greenstein, that can get the middle. And then this is another one that captures the forward scattering peak, but really nothing else. So these are not sufficient to capture what we see in data. And so what we've done instead is we've started fitting the phase function with a spline, because now we can add more parameters because we can go super fast. So this is more flexible. It's not tied to something that's lacking in physical meaning, like the Hennier-Greenstein function, which isn't really based in physics. And with GRaTeR-JAX, we can now fit for the scattering phase function this way. So right now we're doing some model validation to make sure that this new idea of using a spline actually recovers something that isn't just made up by the model. And so this is in the orange, we have the input, injected disks phase function, which we actually used a Hennier-Greenstein for. And then the blue and the dots are the fitted phase function. So the dots are actually the knots of the spline that we're fitting for, and then blue is the interpolation between them. So for different inclinations of disks, you'll have different scattering angles probed. So for a face-on disk, you're going to see fewer scattering angles. You're going to see just closer to 90. And then for a edge-on disk, you're going to see a much larger range of scattering angles. So the pink line is where we started all of the knots in the fit. And you can see that they all reproduce the target phase function quite well. So this is showing that the splines are working, which is really cool. So our first science application of this is to apply it to the Gemini Planet Imager debris disk sample, specifically the polarimetric data, so that we can sidestep the self-subtraction, like I mentioned. Although integrating this with something like PyClip and forward modeling is on our future wish list of things to do. So there have been a lot of analyses of GPI data already. There have been some great uniform analyses by people in this room, Katie Krotz and Justin Hom. But what we're doing now is we're fitting for more parameters, and we're fitting for the phase functions with a spline instead of with a Hennier-Greenstein function. And so this is still a work in progress, but I'm going to give you a couple of little sneak peek results anyways. So these are some of our beautiful disks that we have modeled. The one on the top right is HR4796, which if anyone has modeled disks, it is notoriously an absolute pain. And it actually does quite well. The residuals are not that bad for HR4796. So we can take a moment to appreciate the nice, pretty pictures of disks. It's my favorite thing about studying extended sources anyways. And then this is an interesting plot of two parameters that are not commonly fit for. So on the top, we have the scale height, and on the bottom, we have the flaring parameter. So remember, that's how the disk flares out radially. And so historically, beta is typically assumed to be 1 or 2, and so this was a really big surprise. Across the GPI sample, we see a much larger spread in beta beyond this typical assumption. And in our injection and recovery tests so far, we're able to, retrieve negative values of beta for, disks that we make that have negative values of beta, so we don't think this is an artifact of the model. And yeah, some of these have a negative value of beta, which implies that the disk, instead of going out, goes in, and that's something we're still trying to make sense of. But it's a fun surprise that we got from this. So our approach to dealing with the GPI data with this was leave everything free, see what happens, look at the degeneracies. Yeah, just try it out, because we can now. And this was a fun surprise. Because we have, big corner plots for all of the disks that we fit, we can now actually see where some of these degeneracies are happening. The scale height tends to be one that is degenerate with a lot of other parameters from what I can tell so far. But we still have a lot more to look through in these. I have many corner plots. So the takeaways here, GRaTeR-JAX can do disk modeling super, super fast now, thanks to GPUs and these other techniques. The package is open source on GitHub now, and we're hoping to submit a paper to the Journal of Open Source Software soon. And the first experiments with this package on real data are proving to be quite interesting. So I didn't show it, but from our initial testing, the spline SPFs look actually quite similar across the sample, which is something that has been noticed in previous works, that things look like they might actually tend towards a sort of common SPF, and we're seeing that too. Some parameters we assumed to be constant are actually quite varied, which is interesting. And we can now see some of where there are degeneracies. So there's a lot more work to do, both in analyzing the GPI sample and applying this to a bunch of other archival data out there. So there's a lot of work I'm very excited for. And if you're interested in trying it out, GRaTeR-JAX's first pre-release is on GitHub now. So it's at this QR code. And we're definitely happy to have people beta test it. We would love to see how it goes for you. And then since this talk uses GPI data, I also wanted to share 2 QR codes that are related to GPI 2, which you'll hear more about in Bruce McIntosh's talk on Thursday and some other talks and posters throughout the week. We have a community survey that is, gauging what you guys want to see from GPI 2.0. And the collaboration has an open call for members if anyone wants to join us. So with that, I'll take any questions.
Hi, Aniket Sanghi from Caltech. Thanks for the great talk. So I was curious for the beta parameter, the assumptions, are they purely based on theory, or have there been disks observed with that specific beta parameter that justifies those assumptions?
Yeah, so asking if there are disks observed with that specific beta parameter is tricky, because in order to get a value of beta for the disk, we have to model it and fit it. So this is an assumption I think is mostly based in theory, and does make sense. But yeah, isn't something that's been confirmed observationally.
Marcus Bonser from ESO. So now that you have a differentiable model, have you also started looking into changing the optimization for the MCMC itself? So there's several methods which use the gradients, like Hamiltonian Monte Carlo, and packages like Pyro, which you could use to speed up the optimization itself on top, because you have the differentiable model.
Yeah, we started playing around with the HMC. It's not in the polished version that definitely works so far, but it's definitely on our radar as something to try.
Hi, great talk. Have you looked at connecting the variation you see in the beta parameters to anything physical, like the spectral type or the age of the system? And can we learn something about disks in general from that?
Yeah, so once all of this fitting is done, trying to look for trends is something that I'm definitely interested in doing. Part of the catch there is that there's not a ton of spectral type diversity amongst this sample. So this is, from GPI, where we were with a lot of high contrast imaging instruments, have been limited to brighter stars because of AO limitations. So that's changing now. And so we could theoretically do this on a bunch more things from different instruments and get a more diverse sample in order to look for trends, which is something that I want to do, but might not be super possible with GPI. But I'll look for trends in what we have.
Hi, really nice talk. I think you made a really convincing case that the splines are better than the Henry-Greenstein function that we've been using for years. But I was wondering if there's any prospects to really use a physics-driven model for the SPF, or if we're still doing it more empirically for the foreseeable future.
Yeah, that is not something that I am personally thinking about right now. I know that there have been a couple papers that have tried to tackle, reproducing phase functions with more physics, but I think it comes down to scattering physics is hard. And so I think that's something that would be great for us all to work towards, but it is not on my immediate radar.
Okay, thank you.